We've seen how to calculate the precise slope at the t equals 10 point. How do we calculate the slope at an arbitrary coordinate t, at an arbitrary clock time t? How do we get the rate at which y changes with respect to t at just any time, clock time t? Well, we start by thinking of 2 points just as before. We're going to call the coordinates of this point t and y of t. Now y of t, remember y of t is just function notation. If y equals at squared plus bt plus c, then that's what y of t is. If we know a, b, and c, we've got specific numbers and we've got a specific formula for y of t. This point we're going to call t plus delta t so that we have a run of delta t. Let's go ahead and put that in here, delta t. Okay, we have a run delta t from here to here between t and t plus delta t. What's the y coordinate here? Well, it's y of t plus delta t. Remember that what's in the parentheses here is what gets substituted for t. That's what we've been doing with this t plus delta t all along. So that we can imagine calculating a slope between t y of t and t plus delta t y of t plus delta t for some delta t. Then we shrink delta t down. Now when we shrink delta t, we get into this little orange triangle. And of course, the 2 points along the curve that define this orange triangle will be, again, t y of t and t plus delta t y of t plus delta t, the same as they were before, except now we think of delta t as being a little bit smaller, quite a bit smaller. Of course, delta t can still get a whole lot smaller. We can shrink this triangle all the way down to the point. When we do, the sloping hypotenuse of that triangle will have a slope that approaches the slope of this tangent line. This tangent line is the line that comes along and touches the graph at this one specific point. It comes closer, closer, touches, then moves further and further away again. It's a straight line that touches the graph right at this point, and it's the limiting slope of the hypotenuse of your slope triangle from graph point to graph point.